Hello everyone, welcome to lesson 6-4, Dilations. Let's get right into it and take a look at our vocabulary startup by identifying what a dilation is. A dilation uses a scale factor to enlarge or reduce a figure. Scan the lesson and complete the graphic organizer. So what is a dilation? Things that are like this. So what's like a dilation? What are some characteristics and things I've already learned and I can use for this? So let's start with things that are like this. Well, we have enlargement when we enlarge a picture, or reduction when we reduce the size of a picture. And we do this sometimes when we do scale drawings or models to represent a larger. We've done this in class before in earlier lessons as well. So what are some characteristics that we can think of? Well, we know that when we make a scale drawing or a model of to represent another, for example, a model car or a model house and so on, we do know that it's going to be a different size, but the shape, it'll be the same shape as the original. So it's essentially the same, but represented in a different size, right? And what are some things I've already learned that can be applied to this? Well, we've learned about ratios, right? So we've learned about the scale factor as well in graphing, where we have to take a relationship between two numbers and increase it proportionally or decrease it proportionally. And that's what a scale factor is for. So if you remember some of these lessons, then this lesson should be easier for you. Now that we've defined what dilations are, let's look at a real-world example. Photography. Nancy wants to insert a photo of her dog on her blog. The current size of the photo is 480 pixels by 640 pixels. So here's the photo, right? And it looks like she wants to maybe create a reduction for her blog of the original picture. Suppose she wants to reduce the photo to 120 pixels by 160 pixels. Compare and contrast the original photo and the reduction. So we're going from 480 by 640 to 120 by 160. What relationship do I see? I do see that I have one ratio here, and that ratio is 480 to 640, or 480 by 640. And then I see that it needs to be reduced to 120 to 160. So I could write a similar one next to it, and I don't know if it's equivalent yet or not, but I'll write 120 right on the dog's head. Sorry. Right over 160, and just see what did I have to do. Okay, how do these match up? So if I double, actually, look at, you might be able to see it already. You see the 12 and you see the 48. 12 times 4 is 48, or you could say 120 times 4 is 480. This is the same thing apply here. 16 times 4 is 64. Yep, 160 times 4 is 640. So what I can tell you is that it's been reduced, okay, divided by 4. It's been reduced by 4. Okay, so you have to be pretty good with your factors and multiples to be able to identify these sorts of relations. So suppose that, what's the question? Compare and contrast the original photo and the reduction. So what can we say? I would say the dimensions of the original photo are 4 times the dimensions of the new photo, okay? Or the image, the pre-image to the image. So what is the scale factor from the original to the reduction? It's 1/4, right? It's 1/4. So we literally went down to 1/4. If you were to multiply these values by 1/4, you would get these values. Let's take a look at our key concept for this lesson. Dilations in the coordinate plane. Okay. Words, a dilation with a scale factor of k will be. Okay, so a scale factor of k is identified that we don't know what the scale factor is, so we've just picked a variable, right? An enlargement or an image larger than the original image if k is larger than 1. A reduction or an image smaller than the original image if 0 is less than k, which is less than 1. So this is just a reduction, and this is an enlargement or a greater size. The same as the original figure would be represented with the equal signs. Okay, so that would be a congruent shape. When the center of dilation in the coordinate plane is the origin, each coordinate of the pre-image is multiplied by the scale factor. That makes sense because you want to multiply it by the same. So you see how here it went from AC, it's only 2, 1, 2. Over here it's 1, 2, 3, 4. So it's doubled. If this is 3, 1, 2, 3, this needs to be 6 from here to here. Is it? 1, 2, 3, 4, 5, 6. It is. Okay, so there you go. And then you have your hypotenuse, which needs to just connect B and C. The pre-image and the image are the same shape, but not necessarily the same size, since the figure is enlarged or reduced by a scale factor. And that's what we're solving for. We're solving for those scale factors. Let's take a look at the first example. A triangle has vertices A, 0, 0, B, 8, 0, and C, 3, negative 2. Find the coordinates of the triangle after a dilation with the scale factor of 4. So it looks like we are quadrupling our size, right? The dilation is, again, when we multiply a number by a whole number, our number is going to increase. But if we multiply by a fraction, it's going to decrease. Don't forget that. The dilation is x, y become 4 times x and 4 times y. So as you see here, these multiply the coordinates of each vertex by 4. So here we go. 4 times 0, 4 times 0 is still 0, 0. But B becomes 4 times 8 and 4 times 0, 32, 0. And C becomes each coordinate, the 3 and the negative 2 as we have up here, will also be multiplied each one times 4. 4 times 3 and 4 times negative 2 become 2 and negative 8. So the coordinates of the dilation are as follows. Okay? So you see that they've just been quadrupled in size. Now if you think you got this, and I believe you do, it's quite straightforward, you can go ahead and pause the video and try a dilation scale factor of 2. So you're going to take this 2 and multiply each coordinate or each order pair by 2, and then you can give me the new image of, or the new coordinates for your shape. Alright, I hope you paused the video and you tried it out so that you can see the answer. So what I'm going to do is I'm going to take each one of these and I'm going to multiply each coordinate by 2 as mentioned here. So when I'll start with W. And for W, I have negative 2 times 2 is negative 4. And I have 4 times 2 is 8. And then I have, and then for X, we're going to do the same thing. We're going to take our 1 right here and multiply it by 2. So 1 times 2 is simply 2. And then we take the 4 right there and we multiply by 2. And that gives us our 8, right? Our 8. We continue on with our Y, and the first coordinate for Y is 3, so 3 times 2 is 6, and negative 1 times 2 is negative 2, right? And then finally, our Z, or Z, right there, okay? And we're going to multiply negative 3 times 2 is negative 6, and negative 1 times 2 is negative 2. And there you have it. That's an ugly 2, but I couldn't fit it in there. I hope you got this correct. Okay, now let's look at a dilation where the size is actually reduced. Okay, where it's decreased in size. Let's see over here, because it looks like we have a scale factor of a half. So anything multiplied by half, you get half of that number, right? So if I were to multiply 3 times a half, I get 1 and a half. 8 times a half, I get 4. 10 times a half, I get 5. 6 times a half, I get 3. You get the half of each number, you get it? So then I have 8 times a half, and I get 4. 2 times a half, and I get 1, right? So if that's the case, let's see if they match. So I said J should be 1 and a half and 4, and there it is, 1 and a half and 4. Now it's being written in the proper fraction format, all you have to do is just ask yourself how many 2's are in 3, and you know that there's 1. And what do you have left over on the top to get to 3? You have 1 left over, again over 2. So 3 over 2 is 1.5. And you're going to see that it actually moves 1.5, right? X runs 1.5. You see it right there. 1.5, 1, and then a half, okay, to 4. Or 1.5, 1.5, 1.5, and 4. But don't forget that we are reducing the size. So essentially, this was our image, and we are reducing our size from the point of origin. Okay, from the point of origin, these were my coordinates, 3 and 8, right? So I went 1, 2, 3, and 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. That's my original one. And we're reducing from the point of origin. So now my new coordinate for J is 1.5, 1.5, right in between the two lines there, and then 4 up. 1, 2, 3, 4. And that's how we get that. Okay, I hope that makes sense to you. Continuing on, we said that half of 10 and half of 6 is, half of 10 is 5 and 3, right there. Okay. Half of 8 is 4, and half of 2 is 1. And there it is, 4 and 1. Okay, so then you can see how the math was done. Each number was multiplied by half to give you half of that number. So what do we learn from this example? If we could make a conclusion, I would say that if the scale factor is it's greater than 1, so a whole number greater than 1, the dilation is an enlargement. The shape's going to get larger. If the scale factor is between 1 and 0, so a fraction, the dilation is a reduction, because anything multiplied times a fraction will be reduced. Okay, I hope that makes sense to you. And here's some practice for us. If you think you understand it, please go ahead, pause the video. Now you will be asked to do a dilation with a scale factor of 3, so you know it's going to be an enlargement. It's a number greater than 1, it's a whole number, and so it's going to enlarge. It could also be a mixed number and would be an enlargement, but I'm just trying to let you know that it's not a fraction, so it's not going to be a reduction. It's going to be an enlargement. It's going to become larger. But this time you're also being asked to draw it. Okay, so use your coordinate plane and draw your pre-image, and then solve by factoring it all to 3 and draw your image, your new image. So go ahead and pause the video and try it. Okay, I hope you paused the video. After some serious effort, I was able to draw my pre-image. It doesn't look great, but that's the best I can do on an iPad. And you can see that I have F, G, H, and I. I've labeled it. Now I'm going to take all of my ordered pairs and multiply them each by 3. After multiplying each one by 3, here are my new set of coordinates. So now I have -3, 3 for F, for my image for F. So I go -3, 1, 2, 3, 3, 1, 2, and 3. So it's right there. And for G as well, working from the middle, I get 3 and 3, 1, 2, 3, 1, 2, and 3, right there. Okay, so I'm just going to draw it so that you can see how it looks. Okay, and you should have something that looks like this. Don't forget to label it as well with your new labels, differentiating from the old ones. Okay, and that's what I'm doing right now. All right, I hope that made sense to everyone. Example 3. Through a microscope, the image of a grain of sand with a 0.25 millimeter diameter appears to have a diameter of 11.25 millimeter. What is the scale factor of the dilation? So in real life, it's this large, right? Through a microscope, the image of a grain of sand with a, okay, that's the real size, and then through the microscope, it becomes this much larger. So what's the scale? So write a ratio comparing the diameters of the two images, okay, the diameter in dilation and the diameter in originality. Remember to write the one in the bottom so that you can actually divide, and you'll notice that because it's becoming larger, you're going to get a large solid number, whole number. If the smaller number was on top, you would get a fraction, right? That would mean that it's being reduced in size, and like this, you know, it's being increased in size, right? Because you're going to get a whole numbers like this. So the scale factor for the dilation is 45 because it's being increased in size. It's going from this small to this large. All right, last example. Lucas wants to enlarge a 3 by 5 inch photo to 7.5 by 12.5 inch photo. What is the scale factor to the dilation? Essentially what we have to do is, let's write this down as a ratio, right? So we have a ratio there, and we know that we're going up to, the 3 will become 7.5, and the 4 will become 12.5. So we have to figure out what it is that we have to do to go from this size to this size, and from this size to this size. You obviously know when you go from a smaller number to a larger number, you're multiplying. But when you go the other direction, you are dividing, right? So let's see. If I divide 12.5 divided by 4 or 7.5 divided by 3, what do I get? Or you could write it like this, as I've done here. We have our 7.5, and we're going to divide it by 3. So I'm going to figure out how many 3's I have in 7.5. I know I have 2. And what am I left with? I'm left with 1.5, right? Because 3 times 2 is 6, and I'm still left with 1.5 left. So that would mean that this would be a scale of 2.5. 2.5. Let's see if the same thing happens when I do it from the 12 to the 4, right? So, oh, not 4. Sorry, I wrote that wrong. It's 5. My mistake. I just noticed it. Okay, so when I do that and I have my 12.5 to 5, I have to ask myself the same thing. How many 5's are in 12? I know I have 2. And what do I have left over? 2.5. 2.5 is half of 5. So again, it's 2.5. And there you have it. My scale factor is 2.5. And finally, here's our guided practice. Take a look through it. Make sure you feel comfortable with the content. And if you have any questions, please bring them to class. See you then, everyone.